So yeah, my title of my talk is It's a Trap, and I'm going to tell you a little bit about how to trap an atom, and towards the end about why you might actually want to do this. So first of all, let me remind you about what atoms kind of look like, a model for an atom, which is that we've got positive charges in the nucleus of the atom, and we've got negative charges, electrons, that orbit around this positively charged nucleus. And typically, for most atoms, you've got an equal number of positive and negative charges, so the total net charge of the atom is 0. But you can kick off one of these electrons, and if you do that, then you have a net positive charge, because you've got one less negative and the same number of positives you had before, so you've got an overall net charge that's positive. And you can do this in a number of different ways. So if I take my neutral atoms, which are depicted here by the yellow balls, I can fire an electron at it, and then doing that, knock off one of the electrons from the atom, leaving a positively charged atomic ion. I could also use light to do the same thing. Take light, hit the neutral atom, and knock off one of the electrons. Again, get a positively charged ion. Or you can do this sort of Star Wars style feature with laser light and take a big pulse of light and blast a material, and in doing so create lots of ions in the process. So this last method is the one that we currently use in my lab here at Denison to make atomic ions, these positively charged particles. Okay, so once we've created them, we want to trap them. And so I want to tell you a little bit about how you can go about trapping a charged particle. So first, let me remind you a little bit about charges in general. So if I have a single negative charge sitting here, it creates an electric field around it. So that's depicted by the blue lines here. And the arrows point to where the force would be, or what kind of a force would be experienced by a positive charge that you sit next to this negative charge. So if I take a positive ion, for example, and I set it next to this negative charge, it'll feel force in the direction towards the negative charge. So opposite charges attract. Similarly, if I take a positive charge and instead, this also creates electric field lines, but now they point in the opposite direction. And so here, if I now take a positive ion and stick it next to it, what happens is I get a force in the opposite direction, so like charges repel one another. And so using this feature of that opposites attract and like charges repel, we can try to control the position or the motion of this positively charged particle, this positively charged ion. And so I want to just demonstrate how that can work. If you have, for example, a positively charged thing, so this is going to be a rod, I could charge this up by rubbing like a piece of wool against it or something and give it a static positive charge, but this has a belt inside of it that does that for me with a battery, so I can do it much more efficiently. So I'm going to positively charge it, and in doing so, I'm going to also apply charge to this film that's getting positive charge on it as well, and now I can make it fly, right? So I can levitate it because the positive charges repel one another, and so I can make it sit there, right? Or I could push it to one side, or I could push it to the other. So using this positively charged control rod, I can control this positively charged thing up here. Now, it's not really trapped, because if I just hold the control rod in one spot, eventually this moves off to the side and falls down. So in order to trap a charged particle, we need to go a little bit more effort. We need more than just one control rod. And so what you might think initially is, well, why don't I just take my positively charged ion and surround it with positively charged control rods? So I'm going to put positive charges here, 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 and here. All of those then create electric fields, right, that point away from those positive charges. And initially, it seems like this could potentially work. However, it turns out that electric field lines are, in a sense, like water. What goes in also has to come back out. So this actually doesn't work, because if you tried to take like hoses, for example, and you're trying to trap a ball in the middle of the air, and you shoot water in it in all directions, that water has to shoot out as well, and the ball can then follow the water that's shooting out. And the same thing can happen here. So this positively charged ion can follow one of these electric field lines out, and it's not trapped. So just a static configuration of positive charges around it actually doesn't work. So instead, we have to be a little bit more clever, and we're going to instead surround it not just with positive charges, but a combination of positive and negative charges. So initially, then, this creates an electric field that looks like this. We've got it pointing away from the positive charges and pointing towards the negative charge. So it's sort of trapped in the horizontal direction, but not in the vertical direction, right? Because the positive charge wants to move towards those negative charges. But before it moves very far, I'm going to switch them. So we're going to switch the direction very quickly, and by swapping it back and forth very fast, going between positive and negative very quickly, you can actually create a trap then for the positively charged particle. And so here's a model of what that looks like. This is what a trap might look like. Those red dots in there are supposed to be my positively charged ions. And I take two of these control rods, the ones labeled RF voltage, and I'm going to apply some voltage to them, switch it back and forth between positive and negative, basically between positive and negative charges very quickly. In the case of atomic ions, we're talking about a few million times per second is how often we switch it back and forth. And in doing so, we create what's known as the potential here for it that's shown up here. And at any instant in time, it looks like it's anti-trapping in one direction. In other words, if I took a ball and I were to set it on this saddle-shaped thing, it would roll off the side at any instant in time. But by flopping it back and forth at the right speed, you can actually trap it, okay? And this actually works in the analogy, the mechanical analogy of putting a ball on a saddle as well. And so that's what I want to try to show you next. And this one's a little tricky, so it might take me more than one shot to do it. But up here I've got a saddle, which you can see that I can rotate, okay? So if I just take a ball, of course, and set it on here, it's just going to roll off the side, right? But if I spin it, and it's attached to an electric motor, so if I spin it around, then I should be able to take the ball and set it in the center here. Oh, let me try that one more time. I've got a video of this also in case this doesn't work. There. So then you've got a trapped racquetball, right? That stays in place. And so now for a ball, of course, I could just take a bowl, but for a charged particle, this is the best way that we can do this, is to switch it back and forth very quickly with this mechanical analogy. Okay, now let's zoom in and actually see what that looks like in a little more detail. So like I said, I've got a video of that. So here's what this looks like when the ball is trapped. So it's going back and forth, it's staying trapped in the saddle. If I slow it down, you can actually see this motion in a little more detail. So you can see that the ball is trying to roll off the side at any instant, but before it gets very far, the saddle has rotated into that new position and pushed it back towards the center. And so in doing so, it still just sort of oscillates back and forth, rolls back and forth in the saddle, but it stays confined to that space. It stays trapped. Okay, so the next thing I want to show then is that we can actually do this with charged particles, not just with a ball on a saddle. So I've got up here a charged particle trap. This is not for atomic ions right now. I'll show that in a moment. But this is going to be for charged dust particles, in particular charged cornstarch particles, okay? So I've got these rods up here, and let me actually show you what I've got so it's a little easier to see. So I've got 4 control rods, which you can see here, and some excess cornstarch on it. I'm going to turn some voltage on 2 of those rods that swap back and forth, now at about 60 hertz, and it's about 6,000 volts, but it's very safe. It's current limited, so it's perfectly safe. And then if I apply some cornstarch to it, and that is charged up. Oops, let me turn on the laser here so you can see it. There. And now you can see the trapped cornstarch particles in that particle trap. So we've got, again, high voltage on 2 of these rods, like let's say this one and the one that's behind this one. So there's 4 rods in total. And they're swapping back and forth at about 6,000 volts. And we have these trapped charged cornstarch particles now suspended in air. So this works for charged particles as well. And it works not just for cornstarch, but it can actually work for atomic ions also. Let's switch back to that. Okay, so there's the picture of the whole trap where you can see a string of trapped cornstarch particles. And this is what it actually looks like in the lab when we do it for atomic ions. So now the trap is contained under vacuum. So we've taken out all of the air. So it's almost a perfect vacuum. It's about 10 to the minus 11 torr, if anyone who's familiar with pressure units. And we've got the 4 control rods again, 2 of them of which have voltage applied to them. That's switching back and forth between positive and negative very quickly. In this case, again, a few million times per second. Those are the ablation targets where we're going to hit with the laser to produce the ions that I mentioned at the beginning of the talk. And in doing so, then, we can trap and confine a cloud of atomic ions, in this case, barium ions. So in the immortal words of Admiral Akbar, it's a trap. All right, so we can trap charged particles, then trap atomic ions, and so the next step then to controlling them very precisely is we'd like to also cool them. And so I'm going to talk a little bit about how we can cool atomic ions and why this is interesting. So first of all, let me give you an idea of what temperature scales I'm talking about here. So I'm going to talk primarily in the Kelvin temperature scale. And so to give you an idea of what that is, right, this room is about 295 Kelvin, or about 70 degrees Fahrenheit. Right? If you go hotter, water boils around 373 Kelvin, and the surface of the sun is up at 6,000 Kelvin, or about 10,000 degrees Fahrenheit. Okay, so this is a logarithmic scale, so each tick mark here represents a factor of 10 in temperature. Okay? Now going the other way, if you get colder, water freezes at about 273 Kelvin. Air liquefies is about 77 Kelvin, that's negative 321 degrees Fahrenheit. And deep outer space is around 2.7 Kelvin, okay? And to give you an idea of just how bizarre these temperature regions are, right, how outside of our normal experience they are, I want to show you what happens to a racquetball when it's frozen down to 77 degrees Kelvin. So a normal racquetball, right, if I throw it up in the air, it's going to bounce nicely. But if we take a racquetball and instead put it into liquid nitrogen, which I brought some, whoops. All right. So we put the racquetball in liquid nitrogen. First of all, the liquid nitrogen boils because, according to liquid nitrogen, the racquetball is boiling hot, right? And after it's cooled down a little bit, and I actually have another one here that's been in here for a while, so I might just pull that one out. So after we've frozen it down, we can see how it behaves now. So if I throw it up in the air now, it didn't break, but it's, there we go. So it behaves very differently than your normal everyday racquetball once it's at negative 321 degrees Fahrenheit. Okay. All right. Now, although that's a lot of fun, that's not actually the main method we're going to use to cool atomic ions. It just gives you an idea of how strange these temperature scales are, how materials and other things behave differently as they get really cold. So let's talk about how we're going to cool an atomic ion. For this, I'm going to use something called the Doppler effect. And if you've never heard of the Doppler effect as a term before, I can almost guarantee you've heard the Doppler effect before, in the sense that for sound waves, this applies to any wave, but for sound waves, if you have a wave coming towards you, like let's say from a siren, from like a fire truck or something, as it goes away from you, so either you're traveling away from the source of the sound wave or the source is traveling away from you, the wave gets to longer wavelengths, which means lower frequency or lower in pitch. And as you move towards the wave, or as the source of the wave moves towards you, it gets to higher frequency or higher in pitch or shorter wavelengths. So that's what's depicted here. So if you remember, if you've ever been standing on a sidewalk, when a fire truck comes past, right, it sounds high pitched as it comes towards you, and after it goes past and it's going away, it sounds lower in pitch. That's the idea here. That's the Doppler effect in action. So we're going to use the same thing, but not for sound. We're going to use for light. So we're going to take our trapped atom, or just an atom for now. We're going to take our atom, and we're going to shine laser light on it. Now, the atom only has particular energy levels that the electrons in the atom are allowed to be in. So I've just showed a very simple picture of that over here. We've got one lower level, and we've got one upper level. And in order to make a transition between those two levels, it can absorb some light to make a transition, but it has to be light that's exactly on resonance, exactly the right frequency, exactly the right energy to make that transition. So if we tune our laser so it doesn't quite have enough energy or not quite the right frequency to make that transition, then when the atom moves, let's say first it moves away from the light, that gets even lower in frequency or lower in energy, so it still can't make that transition between the two levels. But as it moves towards the laser light, it goes to higher frequency or higher energy, and now it can make the transition between those two states. So it can absorb a little bit of the light, and when it does so, it gets a little kick in the direction that the light was traveling, which is opposite to the direction that the atom was moving. So it slows down a little bit. And slowing down also corresponds to lowering the temperature of the atom. So now if the atom is trapped and it's oscillating back and forth in that trap, going back and forth, every time it goes towards the laser light, it gets a little kick in the direction opposite to its motion, and it slows down a little bit. So it slows down until it gets very, very, very cold. So this technique is known as laser cooling. And in doing so then, we can make these atoms really cold about 0.001 degrees Kelvin, which is just a fraction of a degree above absolute zero. So around less than negative 459.6 degrees Fahrenheit. So really, really unimaginably cold. All right, good. So what does this actually look like then with an actual atom? Well, shown here is the level structure now for barium ions, which I mentioned earlier. It's a little bit more complicated than the level structure I showed before, but not a lot. We just need 2 colors of light now instead of 1 in order to do the laser cooling process. These colors, by the way, are made from diode lasers that we've built in the lab here at Denison, and we also create the blue light through a process called second harmonic generation, which I won't get into. But we can create both the blue and red light needed to laser cool barium. What this actually looks like in the lab, in a larger picture, first of all, there's another picture of the trapped barium ions fluorescing under laser light as they're cooled. So this is what the lab actually looks like in Olin, across the way there, here at Denison. There's a number of lasers and optics and other things under the curtains here, and on top there's a lot of custom and both commercial electronics, many of which have been all the custom things here built here at Denison. A little more in-depth view of what's under the curtain here. We've got some lasers over here, a lot of custom parts that were assembled by my students, myself, and Dave in the back there helped machine a lot of the parts that went into these things as well, or did the machining for the parts that went into these things. There's some monitor and frequency locking that goes on here to carefully tune and carefully calibrate everything in the experiment, and then the vacuum chamber of the house is the ion trap is in the back. If I zoom in on that a little bit more, you can see back here we've got the ablation laser that's used to produce the ions, the vacuum chamber that houses the ion trap and the ions themselves, and then the imaging system that we use to create the pictures and actually observe that we have trapped atoms. Okay, now this sort of an experiment also requires a lot of control of all of the equipment that I just showed you. And so we use computer control to do that. Here's just a snapshot of what that program looks like. This is, again, something that I wrote to control the experimental apparatus so that we can control the timing of everything in the experiment, switch things on, switch things off. This is a very simple timing sequence here. As things get more complicated, if you want to do something interesting with the atoms besides just trap them, then the sequences can get much, much more complicated. So let me tell you about some of the interesting things you might want to do with them once you have trapped and laser-cooled ions. So that brings me to the third part of my talk, which is talking about the motivation and some of the applications for this kind of work. So there are lots of different reasons you might want to do this. I've listed a few here. And I'll talk about 2 applications in a little bit more detail. But generally speaking, there are a lot of potential applications for this. Historically, there's been a lot in spectroscopy as we get really fine, really precise information on the atomic structure of different atoms and ions. This informs measurements in things like astronomy and atomic physics and chemistry and material science and lots of other different fields is where this information is used. Trapped atoms are also used to make the world's most precise clocks, atomic clocks. And those are used for a host of different things. There are a lot of really interesting things going on right now with precision measurements that use atomic clocks. And I'm happy to talk more about that if there are questions about that later. And then the other area that I want to focus on in some detail is also quantum information, which is the main motivation for my research. But before I get to that, let me say one other application of atomic clocks that I am pretty sure everyone has used, and that's the Global Positioning System, or GPS. So GPS relies on atomic clocks in order to operate. So there's a constellation of satellites that orbit the Earth, and each of those satellites has several different atomic clocks in it that keep very precise time, and they're all synchronized with one another. And those satellites broadcast information to the Earth, 2 bits of information. One is their position in their orbit, and the second is what time it is. So by broadcasting that information, because the information takes time to travel from the satellite to where it's received on the Earth, if you know how long it takes to travel that distance, then you can determine how far away the satellite is from where you are. So, for example, we take one of these satellites and it broadcasts information. You say, oh, I've received this information and it took 0.07 seconds to get to me from the satellite. You know something about how far away that satellite is. So you know that at that point, then you must lie somewhere on this circle with respect to the satellite. And this is in 2 dimensions. 3 dimensions, of course, that circle is actually a sphere. Okay, so there's a sphere that says I'm somewhere on this sphere now, away from that satellite. And then you can do the same thing for another satellite. Maybe it takes 0.08 seconds. And a third satellite, maybe it takes 0.1 seconds. But once you've acquired a signal from at least 3 satellites, then you can see where do those circles or where do those spheres all intersect. And that tells you where you are on the Earth. So GPS relies on the precision of atomic clocks in order to position things, people, cars, trains, everything on the surface of the Earth. Now, the clocks that are in the satellites do not actually, at least not yet, they don't contain trapped and laser-cooled atoms. It's a simpler version of an atomic clock. But those atomic clocks on the satellite are only stable over short terms, so they have to be constantly resynchronized with clocks on the ground that are based on trapped and laser-cooled atoms that are the most precise timekeepers that have ever been created. And so by synchronizing all those clocks, then it enables GPS to work. And so if you've ever used GPS, you've relied on trapped and cooled atoms before. Okay, so that's one application that I wanted to point out that's been a very important application for atomic clocks in the past. The other thing I want to talk about now is quantum information, which is the main motivation for my work. And I'm going to be brief here, but there are several different areas of quantum information that are being pursued, and this is a fairly new field. So one area that's being pursued is quantum computation, which seeks to use features of quantum mechanics to try to accomplish otherwise intractable computational problems. Things that classical, regular computers, even supercomputers, have a really hard time dealing with. One of those problems is encryption, or rather decryption or code breaking. And so that's been a very important application that could be one application for quantum computers in the future. Another area within the umbrella of quantum information is called quantum communication, which is sort of the flip side to quantum computation in the sense that this offers a new way to send secure information that relies not on sort of the mathematical difficulty of solving a problem, but rather relies on the fundamental quantum properties of the information carriers, in this case, the light that's emitted by something like an atom. And so this offers a new way that's in principle unbreakable for secure transmission of information. There's also another area called quantum simulation, where you can take this really well-controlled system of trapped and cooled atoms and use it to mimic or simulate other less well-understood systems. That has a host of potential applications in the future from everything from modeling new materials to modeling complex molecules that could be used in a range of areas. And finally, all of these rely on fundamental aspects of quantum mechanics, and so you can also view this work as a way to test some of the fundamental aspects of quantum physics as well. Okay, so let me say just a little bit more about quantum communication, since that's one of the main motivations for my work. And to do that, I'm going to say a little bit about how communication in general works. So how do you communicate digitally with a device? Like, let's say you have an email you want to send from your computer that has the word Denison in it. You want to send that email across the country or something. So what happens when you hit send, right? So first of all, that information is stored in the computer in binary, so a series of zeros and ones. That's how it's encoded into the computer. And when it's sent, it travels through copper wires in the form of an electrical signal. Things switching on and off, 1 being an on, 0 being an off. So it's encoded now in terms of this electrical signal. And it might travel through copper wires for some distance, say out of the building and maybe down the street or something, but it doesn't go very far in this form. Eventually, it runs into a light source like a laser, which can be switched on and off then by those electrical signals and create pulses of light. Now, these light pulses, this is how the majority of the distance is covered for the information, is in terms of pulses of light that travel through optical fiber. Optical fiber is like a pipe for light. So it travels through optical fiber, through the ground, or under the ocean, and can travel very long distances in this form before finally at the other end being detected, so we're measuring these light pulses, converting them back into electrical signals, which then are reinterpreted as a series of zeros and ones, and then reinterpreted by your computer, in this case as the word Denison. So this is how communication, digital communication works whenever you send information, basically over any reasonable distance. And this goes for not just sending an email or something like that, but even for wireless communication, like from your cell phone, if you send a text message. it's only wireless or goes through the airwaves over a short distance, basically to the nearest cell tower, before it gets converted back into the electrical signals and goes through optical fiber instead. So this idea of sending information over optical fiber has been crucial to getting information to travel over long distances. And now if you, so let me also say that this information that you send in this way is typically encrypted to prevent eavesdroppers from just looking at whatever your information is. But a sufficiently sophisticated eavesdropper could still break that encryption protocol. For example, if they had access to a quantum computer. But by replacing these classical sources of information like the laser and the light pulses with something that's quantum, like a trapped atom, and the light that's emitted by that trapped atom, then you can use this quantum communication protocol, which is in principle unbreakable, even with the most sophisticated adversary. And so then even they cannot break your encryption protocol. So, all right. So let's see then. So this sounds really promising, that trapped ions are a good candidate to do this, but there's one issue. One of the issues is that if I list all of the trapped ions that have been laser cooled and trapped to date, and that have been considered for quantum information purposes, you'll notice that the wavelengths of light used to laser cool them, and that's used to control the atom, most of them lie in the ultraviolet or blue region of the spectrum, way over here, the short wavelengths. This is a region of really high attenuation in optical fiber. In other words, light doesn't travel very far in optical fiber at these wavelengths. Now, some of them have this other region, this what I'll call this medium attenuation region, which is better, but you still can't go that far. Where you'd really like to be is way out at the far infrared region, way in this region over here, which is known as the telecom region of the spectrum, because this is where the telecommunications industry currently works at. This is where they send light pulses through optical fibers in this region of the spectrum, really far in the infrared. And you can see that none of the ions here that have been used to date satisfy that criteria to have their transitions in this range. And so that's where, that's the main motivation for my work, is we're trying to trap and laser cool a new ion. We'd like to add a new one to this list, which is doubly ionized lanthanum, which it turns out has the wavelengths needed for laser cooling and trapping it right in this telecom region of the spectrum, right around 1400 nanometers. So here's what the level structure for that atom looks like. Very briefly, it's a little bit more complicated than the other atom ones that I showed you, barium. And actually, there's some complication hidden here, which is that each of these levels is actually split into multiple levels as well by something called the hyperfine splitting. But nevertheless, we can, in principle, laser cool and trap this atom as well. We just need a few things in order to use it for quantum information purposes. One is we need to be able to produce the ions, which we've demonstrated using that laser ablation technique I showed earlier. We also need to know exactly what these energy level splittings are by doing spectroscopy in the atom, and we've done that. We've made the first and only measurement of that splitting here at Denison. And then finally, in order to use it for quantum information purposes, we want it really well controlled, which means trapping and cooling it, which is what we're working on now. And so hopefully, in the near future, we'll be able to demonstrate laser cooling and trapping of doubly ionized lanthanum, and then be able to apply it to these really interesting applications in quantum information. So with that, I'd like to end by acknowledging the students that have helped me on this research, most recently Quinn, Raul, and Cornell, who are current students here at Denison, as well as many other students that have worked with me over past summers here and have moved on to other things. And of course, thank you for your attention.